Good morning, class. Let's have a problem to show you the procedure on how to deal with the deflection control. So we are asked to determine the immediate live load deflection of a 4-meter simply supported beam with service dead load and live load of 20 kilonewton per meter each. So the material properties are Fc prime 20 megapascal, and Fy equals 276 megapascal. So our modulus of rupture Fr is already given, so we don't need to compute for your Fr here. But in case this is not given, we can use the formula Fr equals 0.7 squared of Fc prime to calculate for Fr. But since it is already given here in the problem, so we don't have to compute it, okay? So your modulus of elasticity of concrete is 21,000 megapascal, and your modulus of elasticity for steel is 200,000 megapascal. So N is also given, so you don't need to compute for it. If in case it is not given, you can use N is equal to ES over EC, rounded it to the nearest whole integer. Okay, so you round up to the nearest integer in case this is not given. So for the formula for the immediate live load deflection, so we use delta I is equal to 5 over 48 k ml squared over ECIE, and this is actually the general formula. But in case we want to get the deflection only for live load, so we need to solve first this, okay, and then this to get this. Okay, you cannot directly solve delta ILL since live load cannot exist alone, so we need to make a solution based on the difference between delta DL and delta D plus L. Okay, so cannot exist alone. Okay, so the beam is rectangular, so the width of the beam is 300 and the effective depth is 340. We have an effective cover of 60 millimeter, so all the units here are actually in mm. And your AS is given by the value 1000 square millimeter. Okay, so we can start the solution by determining the section properties first, assuming your uncropped properties to be the same as the gross properties. We can easily solve for IG and MCR on the basis of this formula. Okay, so since this is a rectangular section, it's very easy to compute for IG. So this is for rectangular section. And for MCR, we simply make use of the formula F is equal to MC over I. Okay, so we just substitute the M is F I over C. So where your YG here simply the distance C from the extreme tension fiber to the neutral axis. Okay, so since this is a positive bending, so the extreme tension fiber is actually one half of the total depth. Okay, so this is 3 of 40 plus 60 is what? 400. Okay, H is 340 plus 60. Okay, for the location of the neutral axis, in case of crop properties, we need to solve for the transformed area, okay, of the beam. So the transformed area of a rectangular section with positive bending is simply like this, where this is NAS and this is B times uh, KD. Okay, so here your Y is actually your KD variable. So how do you make use of the centroidal determination? So if this is the neutral axis, we just take moments about this fiber here. So this is KD over 2, and this is D minus KD. Okay, so this is the D minus KD there, and this is the area, okay, NAS, while this part here is actually 300 times KD times KD over 2. Okay, so this is the area and this is the distance from the centroid. So it will come up to 300 y a bar squared all over 2. Okay, so computing that, we will yield your KD or Y bar becomes 120.87, and for your rectangular section, your I croc is simply calculated on the basis of this formula. Okay, so this formula is B KD cube over 3 plus NAS D minus KD quantity squared. So substituting the values of B, Y, NAS, D, and Y del, you get 656.77 times 10 to the 6 millimeter to the 4th. Okay, so that's the first step is to look into the properties of your section, the gross and the crack properties. So it's a little bit easier since your beam is a rectangular section and we only have a simply supported beam, so we only need the properties at the midspan. Okay, the next step is to compute for the applied moments. So in the applied moments, we have to consider two stages. The first stage is the consideration of your sustained loadings, and the second stage is your consideration of your total load condition. So again, as I have mentioned in my discussion on deflection control, the sustained loads are equal to the dead load if the percentage of live load is 0. Okay, so when does the sustained load differs from the dead load? When this percentage becomes 0, or sorry, becomes greater than 0, such that we are considering storage and warehouse occupancies. Okay, so you take a note here that for storage, warehouse, or maybe garage, wherein there is a remaining load that is sustained always in the floor. So our percent live load is not 0. Okay, so normally this percentage is 25%. Okay, so how do you get the moment now for the sustained loading condition? So the moment applied, okay, the sustained loads is simply the moment which is the midspan maximum moment WDL squared all over 8. Okay, so you have 20 times 6 fourth squared all over 8, so this is 40 kilonewton meter. So for the total load condition, we simply get it on the basis of the sum of the dead and the live. So this is now the total load condition. So we just add the dead and the live here and compute your applied moment in the total load condition. So it's the same formula but of different value of W. So this is 40 times 4 squared over 8. So this becomes 80 kilonewton meter. Okay, so let's move over to the effective moment of inertia. Again, we have to consider two loading condition. Okay, and we have to bear in mind that the ACI gives us this equation to solve for the effective moment of inertia. Okay, so this is now MCR over MA cube IG, then this is 1 minus MCR over MA cube ICR less than or equal to IG. So we all have these variables, parameters here already computed previously. So all we need to do is to plug it in, no? So better if I compute the ratio cube of your MCR over MAS. Okay, at the sustained condition, this must be at the sustained condition. So MAS is 40, so we simply divide 24. Your cracking moment over 40 cube is 2.216. So you just plug it here, and then 1 minus 216, you plug it here, and then you place your IG. So this is your IG, and this is your ICR. Of course, I removed the times 10 to the 6th there to make use of a manageable decimal places here. Okay, so let's check IG and ICR. Okay, ICR is 656.77 and IG is 16 times 10 to the 6. Okay, so there's an error here on IG. So this is not 1000, but this is 1600. Okay, so that's 1600. So let's recompute this and check whether it's equivalent to 860.51. I think there's just a typographical issue there. So 0.216 times 16 plus times 6569. So 860.51. So I think this is correct, no? It is just a typo error. So this is less than IG, therefore, okay. Okay, for the total load condition, what will change here is the ratio MCR over MAT. No longer be MAS. So you divide 24 over 80 now, so you get 0.027. So everything is the same except this one. So again, this is 16. So you get 682.24 times 10 to the 6. So we are going to use now a midspan value only, IEM, a single value at the midspan. So IEM is therefore equivalent to 860.51 times 10 to the 6 and 682.24 times 10 to the 6. So it means that this is applied at the sustained loading condition, and this is applied at the total loading condition. Okay, so solve for delta I at the sustained, so we simply plug it in. This becomes K. What is K on simply supported? So we know that for simply supported, K equals 1 for simply supported. So that's 1. M is 40. L is 4 meters, so I made this in millimeter. So this is L. And then 5 over 48 is the factor. We get EC is 21,000 times 10 to the 6 megapascal. So this is 860.51 times 10 to the 6 millimeter to the 4. Okay, so let's check the unit. No? So for your moment, my unit is in Newton millimeter. For the length, I have a millimeter square over megapascal. So this is in Newton per millimeter square. And then I have a millimeter to the 4th. Okay, so let's cancel Newton. Millimeter square will be cancelled here, but the remaining 2 there will cancel there. So what remains is millimeter. So my unit now is in millimeter. Okay, so similarly for the total load condition, I simply change the value of my M. Instead of having 40, my M becomes 80. This is the applied moment. Okay, so this is 80. K is still 1. And also your I effective is 682.24. So this is for your sustained load condition, and this is for your total load condition. Okay, so this is 9.31, and then all we need to do is to subtract 9.31 minus 3.69, you get 5.62. By the way, class, why is it that I did not place delta I sustained here? Because they're just the same, no? My delta IDL is simply equal to my delta I sustain. Because what? Because your percent live load is 0. Okay? So this is now our final answer for your first problem. Very simple problem on deflection control. So I'll see you on the next video for the next problem. Thank you very much.